All right, folks, welcome. Chapter 3. And what I like to call this chapter is your geometric awakening. Yes, that's right. We've reached your geometric awakening. The first two chapters are just the setup. That's all it. It's a setup here. So if you notice here, we haven't really talked about that many shapes yet. Haven't really talked about that many shapes. We pretty much just talked about polygons as a whole and triangles and parallel lines so far. And then the whole chapter 1 was just kind of a setup, talking about angles and segments here. We're going to go deep dive here, chapter 3, and talk about triangles very, very closely. Because what triangles are, what I like to call triangles, I like to call them the cell of pretty much all other polygons, all other shapes here. So the cell, what I mean by cell, right, is what do you mean? You're a human being. What are you made out of? You're made out of cells. Cells are the building blocks of living organisms. And triangles, right? Triangles are the building blocks of other shapes, right? Other polygons that have sides to them and whatnot. So if you study triangles in detail, that's going to unlock a whole bunch of things about squares, about parallelograms, about rhombuses, rhombi, about regular hexagons, right? We've already seen regular hexagons are made up of 6 equilateral triangles. So there are a whole bunch of observations you'll be able to make up and things to prove, also most importantly, things to prove about squares, about rhombuses, about parallelograms, and all these other shapes that we'll study this year. Trapezoids go with it. But the key is we really need to understand triangles very well. And in chapter 3, it's all going to be about taking this, is that if we have one triangle, how can we prove a second triangle is exactly the same, right? Exactly the same. Because a lot of shapes are made of, actually, of 2 congruent triangles. Think of a square, right? Think of a square. You all know what a square is. We haven't defined it yet, but a square is made up of 2 triangles that are exactly the same, okay? Exactly the same here. So what we have right now, what we have today is section 3.1. Isn't necessarily going to talk about congruent triangles, although you get to that at the end. You do get what the definition of congruent triangles is, and that is, whew, man, that blows your mind. Just wait for that moment. That's going to be crazy. Oh, I'm telling you, the end of this video is going to get nuts. Anyways, definition of congruent triangles will come up, but the thing we need to talk about that before that is the definition of congruent figures. That is the first definition, and you better believe we're going into that right now. Let's get started with definition of congruent figures. All right, 3.1 congruent figures. Yeah, definition of congruent figures. So, hey, I just said that we're going to give you the definition of congruent figures in a second. You might be wondering, hey, I already know like what congruent figures probably is. It means like shapes that are like exactly the same. But we need to talk about, right, what exactly the same means, okay? Because we actually have only defined, right, so far in the textbook here, chapter 1, we've only defined congruency, okay? We have the definition for congruency of congruent segments, okay? So remember, congruent segments are segments that have the same length, okay? Have the same length. So there's a way to describe things that have the same length in terms of congruency, right? We would talk about segments having the same length. That's a definition that we have so far. Where did the other word congruent come up? What other shapes have we been saying? This one thing is congruent to another thing, okay? Right? Corresponding angles are congruent. Alternate interior angles are congruent. Yeah, right? Like we've been able to say that certain segments are congruent, but we've also been able to talk about certain angles being congruent here, right? Certain angles being congruent here. Okay, so we do actually have this word congruent defined in our textbook already in chapter 1. One for segments, which is determining equal lengths. And then another one for angles, which is determining equals measures, right? How wide it is here, right? So how how open a particular angle is when the 2 rays meet each other at the common endpoint right here. Okay, so we have congruent segments, we have congruent angles, and if we kind of bring those 2 things together, what we get is, drum roll please, the definition of congruent figures. Okay, so congruent figures have the exact same shape and the exact same size, here. So you just saw a pretty sweet demonstration of this, we have 2 shapes over here that have the exact same shape and exact same size, and we had another 2 down here, exact same shape and exact same size. So let's take a look at it a second and take a look here. The gray one is the same shape and same size as the red one. The yellow one here, same shape and same size as the orange one. And you've probably done this before, right? In middle school, you may have observed here, I have this shape. If I can put it on top of another shape and it fits perfectly, those two shapes would be congruent to one another, right? Would be congruent to one another. So let's take a look at this here. Exact same size. Write this down in your notebooks too. Definition. Congruent figures have the exact same size and exact same shape. Exact same shape and exact same size, okay? And then think about what causes this, right? What causes this? This will be a definition that we'll actually use in proofs, definition of congruent figures. And you got to think about why, like, why that works, right? Why that works for this figure being exactly the same as that figure. What caused that? What caused that? Well, maybe let's pause for a second and look at these two, okay, these two shapes right here, and quickly just notice this here because oftentimes I get a split audience here, right? When I'm doing this in class and I ask, guys, are these two shapes congruent to one another? What do you think? Are these two shapes congruent to one another? Well, do they have the same shape and do they have the same size? Well, their size looks about the same, right? Size looks about the same. They're like, you know, this length is about the same as that length, and you know, they're one's not noticeably bigger than the other, so it looks like the same size. What about the same exact shape? Okay, same exact shape. Well, if I took this, would I be able to line this up directly on top of this thing right here? If I just slid it over? Well, I don't know. Well, this guy looks pretty close to this guy right here. This guy looks like pretty close to this guy right here. So what am I pointing at? I'm pointing at segments. Interesting. Segments here. It turns out that these two shapes would actually meet the definition of congruent figures, okay? Because in addition to kind of sliding figures over to see that they're exactly the same, this is something that maybe you studied in middle school a little bit. If I rotated this guy here and slid it, boom, those would actually have the exact same shape and exact same size. So I ask you, right, those are congruent. They're good to go here. What do we know about congruent shapes? How can we actually rephrase this a little bit here? Because I want you to rephrase this in your notes a little bit here. Congruent figures have the exact same shape and they have the exact same size. So tell me, right, like tell me, what do you know about the parts of these two shapes here? Why do they have the exact same shape? Why do they have the exact same size? Why? Well, what do you think? How can you describe this? What can I say about this here that makes it exactly the same as this one here? What do they have in common? They have the same what? Well, in order to go on top of that one, what do we know about those two angles that are right on top of one another? What do we know about these two angles that are on top of one another? What about these two angles that are right on top of one another? What about these two angles? Those angles are all congruent. And these sides, look, that side goes on that other side right here because it's congruent. This side is congruent to that side. And this side's congruent to that side. And this side's congruent to that side. So all angles are the same and all side lengths are the same. That is the big takeaway of the definition of congruent figures. And so these are any statements, right? Statements in a proof that you can make using definition of congruent figures. You can say that if you knew, right? So two figures are congruent if and only if they have the same size and same shape. What that is going to allow you to establish is that if you know you have two figures that are congruent, then any of the angles would have the same measure. Any angles would be corresponding angles would be congruent to one another, okay? Would be congruent to one another. And if you know that those two shapes were also congruent to one another, they would have the exact same size, okay? So angles, right? Angles control the shape. And then side lengths, that controls the size, right? That controls the size. So we know that the corresponding sides would have the same length. Sides would have the same length. Okay, so there's my introduction there to definition of congruent figures. Congruent figures have the exact same shape, right? Exact same shape. And this is sort of determined by by angles, okay? So you could have a triangle here, okay? Triangle here, this angle, and 1, 2, 3. Oh, I'm drawing it kind of messed up here. And let me do a bigger triangle. Okay, you could say potentially, right, if these two triangles had the same angles, okay, these would have the same basic shape, but different size. So different sides. So these would be not congruent, right? Not congruent, okay? Not congruent here, okay? Not congruent here. What's different about these ones here? What's different about these ones, the way that we kind of traced over them and kind of gone before is that, oops, right? And something like this, okay? These, right? These are congruent figures right here, boom, because these angles are congruent to one another and right? We have 3 congruent angles, for instance, in this triangle, and we have 3 pairs of congruent sides. That is the deal with congruent figures, is that everything in common is going to match up, right? Is going to match up here. Boom, these 2 angles congruent, these 2 corresponding sides congruent, these 2 corresponding sides congruent, these 2 angles are congruent, this angle congruent to that angle, that side congruent to that side, okay? So that's all it is, right? This is all it is here. Congruent figures, all of the angles are congruent to all the other angles in a figure, right? So remember, we had congruent angles in chapter 1. Now we're talking about congruent figures. All the angles all match up, and then all the side lengths all match up too. All the side lengths have to be congruent as well in order for those figures to be congruent, okay? Big wind up there, but it's an important thing because we're going to get to congruent triangles in a second. That is going to be a big moment for you here in the future, okay? All right, so let's check this out right here. Just let's get some practice on using this one in a proof here, okay? Using this one in a proof here. We're talking about definition of congruent figures. If I knew, for instance, boom, we got these quadrilaterals right here. I got quadrilateral ABCD, and I have quadrilateral X, Y, Z, W, right? X, Y, Z, W right here. If it was given to me in a proof, quadrilateral ABCD is congruent to quadrilateral X, Y, Z, W, what are some things that I can conclude? What are some things that I can conclude here? Well, if we check it out here, quadrilateral ABCD, well, A looks like it's the same measurement as X. Look, A and X match up. Okay, interesting with that. B looks like it's the same angle as Y right here. Y here. Oh, look, B is the second position. Y is in the second position right there. Okay. Z, right? Z and C match up, right? Z and C match up. They're in third position. So anyways, the conclusions we can make is if I knew that this figure were congruent to that figure, if that were given to me, then my conclusion is, right? I can say all of those angles are congruent to one another here. D goes with W, right? D goes with W. Those must be congruent to one another because all the angles in this triangle are congruent to their corresponding angles in that triangle. Not that triangle. These aren't triangles. These are quadrilaterals in that quadrilateral right there, okay? And the position of this is going to matter. So this keeps using this corresponding word. We're going to talk about corresponding, right, where the angles are corresponding. We'll do that in a couple slides here, okay? So if I knew that these 2 quadrilaterals were congruent to one another, I would know that all their angles are congruent, and of course, I would know all the sides were congruent as well, or the sides had the same length, right? Same length, therefore it made it the same size, right? Same shape and same size. There's your definition of congruent figures. So I see a double-headed arrow, just as a reminder, any definition, right? If I knew that these 2 quadrilaterals were congruent to one another, I can conclude any of these, or I can conclude that any of these angles were congruent, right? Based on how they correspond here. And I can also conclude that the sides are congruent, okay? But if I also knew, for instance, that I had all 4 of these angles were congruent to all 4 of these angles here, and all 4 of these sides here were congruent to all 4 of these sides here, that would be enough to conclude that the quadrilaterals were congruent to one another. So just want to remind you of that there. The definitions are if and only if statements, right? Quadrilateral ABCD is congruent to quadrilateral X, Y, Z, W if and only if all the angles are congruent and all the sides are congruent as well, okay? That was a little bit quickly here. We got to get some practice. We'll get some practice later on this one here. All right, section 3.1. For now, all corresponding parts. Okay, so this is the idea is I want to show one figure is congruent to another figure. What do I got to do? I got to show all the angles in one figure are congruent to all the angles in another figure, right? And so like this one's congruent to that one, and that one's congruent to that one, and that one's congruent to that one. I got to do that. I also got to show that all the sides, right? All the sides are congruent as well. And what these are called corresponding parts. So let me write that down as another definition here. Because we're going to toss this around, guys. We're going to toss this around here. Corresponding parts, right? We got to think of corresponding parts of a shape. What are corresponding parts? Well, parts are the angles and sides, right? Angles and sides here, okay? So in order to prove that two figures are congruent to one another, we got to say all angles and all sides. The parts of a figure, parts of a polygon are the angles and the sides. And when we see parts, that's what we're talking about, all right? And corresponding means appearing in the same place in 2 similar situations, okay? Corresponding. So you have corresponding parts. You got to show the corresponding parts are congruent. So obviously, A corresponds to D right here. They're congruent to one another. And then look, AB and AC, right, which would be corresponding to DE and DF because, right, A is the angle in between, right, AB and AC, and D is the angle in between DE and DF. So that means DE and AB need to be the congruent ones, and they are, right? And they are here. Okay, so anyways, corresponding we'll get to in a second here. But once you have this, right? Once you have this, this is how we would prove that these two triangles were congruent to one another. For now, right? For now, this is how we congruent. And do you think there'll be shortcuts later? You think there'll be shortcuts here? Do I think you need to prove, like, right? I'm gonna have you guys write proofs where you write that 2 angles are congruent, and then 3 angles. You got to prove all the angles are congruent. They got to prove all the side lengths are congruent. No, that's going to be too much work. There's going to be some shortcuts coming later. All right, heck of an introduction here, guys. Heck of an introduction. Just kind of give you a big overview. Do some problems, hang out, do Jamboard in a couple days here. But anyways, let's check this one out here. Corresponding vertices name a congruence between shapes. Okay, so this is another thing to talk about here. All right, so here we have some congruent figures. We're talking about triangles. We haven't really done it. Yeah, we've done a little bit here. We've shown the triangle symbol right here. What this stands for is triangle ABC. Okay, so triangles do get a figure, right? Do get a symbol here. So when I see this triangle symbol in front, I mean triangle ABC. Okay, triangle ABC. So this one here says triangle ABC is congruent to triangle DEF. And if I knew that triangle ABC were congruent to triangle DEF, here are some things that I would be able to say. For instance, I'd be able to say angle A and angle D were congruent. Okay, so corresponding vertices name a congruence between shapes. If I knew triangle ABC were congruent to triangle DEF, angle A would have to be congruent to angle D because look, that's the first letter mentioned, right? First letter mentioned here. So angle A and angle D are congruent to one another. Right, congruent to one another here. And then what would I have to know about angle B and angle E just based on how this is listed here? Well, angle B and angle E would have to be congruent to one another here. Okay, so just wanted to point this out here that the ordering when you do name a congruency, so triangle ABC is congruent to triangle DEF, angle A corresponds to angle D, and therefore we would know that those two angles would have to be congruent because the whole shapes are congruent here, okay? So angle B, let's go to angle B right now. So angle B and angle E, what can we say about angle B and angle E? Well, they appear second here in the triangle ABC and triangle DEF. So we know the two triangles are congruent to one another. So that means that angle B and angle E would have to be congruent. So angle B corresponds to angle E, okay? So when we're talking about triangles, let's compare triangle ABC to triangle DEF. What we're doing is we're comparing angle B to angle E, because of the way it's written, right? ABC matches up to DEF, it matches up in that order, okay? So we're talking about triangle ABC being congruent to triangle DEF. What we can conclude is that angle C, it corresponds to angle F, therefore those two angles must be congruent to one another. And visually we see that too, right? We see that too. We'll get some practice in a second here. What would triangle BCA be congruent to? Okay, so just wanted to notice this here. Note this out, actually. Guys, remember, we can name any polygons in order of their vertices, right? In order of the vertices. So I could have called this blue triangle right here. I could have called it triangle ABC, but I also could have called it triangle CAB, right? CAB, because those are consecutive vertices as well, CAB. I could have called this triangle ACB, right? Triangle ACB, because I could have gone the other way around. The way I've named it here, I could have called it triangle BCA, right? Triangle BCA, because they're consecutive vertices here. So if I were to say, like, look at this, let me give it to you that these two triangles are congruent and they're drawn as close to scale as possible here. If I said in this problem here, triangle BCA, because it might be a common problem to give you here, triangle BCA is congruent to what triangle over here? What would I have to name this triangle right here if I wanted to say that this triangle is congruent to that triangle here? Well, B corresponds to what? B corresponds to E, right? Those look like they're two congruent angles. C corresponds to F. So I would have to call this triangle. Well, D goes to A, right? And that would be my last letter. E goes to B. That would be my first letter. And C goes to F. That would be my middle letter. So let's just wrap it up right here. I think we got it. So we got to go with B goes to E. So E is the first letter. F is the second letter. And D is the third letter. Kind of dragging that one out right there. Okay. So just wanted to show you that. Last slide, right? We called this triangle ABC congruent to triangle DEF. We can talk about the same triangles, right? We can name them differently if we want to, but it needs to follow us with it. Right, the correspondences need to follow here. So instead of triangle ABC congruent to triangle DEF, this we could call it triangle BCA. It's congruent to triangle EFD. Hopefully that makes sense. Hopefully that makes sense here. If not, you'll get some practice on this in the problem set here. All right, so in order to name a congruence, the corresponding vertices must correspond to one another. in the naming of both figures. The naming matters, okay? That's why I call it out here. The naming matters, the ordering matters. So keep an eye out for that when you get into your problem sets here. All right, given incongruence, we can also determine how the sides, oh, interesting, okay, we can determine how the side segments correspond to one another, okay? So say this is given to us. Say that we know it's given to us that triangle ABC is congruent to triangle DEF, okay? It's congruent to triangle DEF. Let's check this one out here. Triangle ABC is congruent to triangle DEF. What can we say about the segments? What can we say about the segments? Visually, I think we can sort of jump to the conclusion of what sides would have to be congruent to one another. But let's just try to just look at the way the triangles are named here, okay? What can we say that AB is congruent to, for instance? Well, let's get the triangles out of the way to make this a little bit harder for you guys. You should be able to do this without the triangles. I think you'd be able to guess what this is here. All right, somebody tell me, what are two congruent segments based on the way this is written? Well, we know that A corresponds to D and B corresponds to E. So, for instance, AB must correspond to DE, right? AB corresponds to DE. So check it out here. The way that the triangles are named can actually allow you, just looking at the triangles, can allow you to write down what sides you'd have to know are congruent, okay? So if you're taking notes, you're paying attention to this, it's going to save you. It's going to help you later to just see triangle XYZ is congruent to triangle DEF, then XY equals DE, for instance, and whatnot here. Okay, we'd also know that BC and EF, right, correspond here because look, those are angles that are consecutive, right, vertices that are consecutive, so they would be connected by segments, and they would have to be the same length too, if we knew the two shapes were congruent to one another. Finally, what's the last correspondence here? We talked about AB, we talked about DE, we talked about BC, we talked about EF. What are the final sides here? Well, DE and AC. So this is kind of the interesting, the one that people forget about. If I didn't show you these actual diagrams here, how do I know that AC and DF would be congruent to one another? Segment AC and segment DF congruent to one another? Well, they appear first and last in the actual triangle itself here, okay? So don't forget, a triangle has three non-collinear points connected by segments. So yeah, one point needs to be named first and last, but they would still connect to one another, right? Still connect to one another, even though that D is far away from F in the name of the triangle here. It goes segment FD and segment CA would be congruent to one another because they correspond based on the way that the triangle is named here. All right, oral practice time. I know that was a heck of a lot of introduction, a lot of talk about there at the beginning. So that was a long I do. Now it's a we do right now. Check this one out. Oral practice. Match the corresponding parts of these triangles here. Now, is this too easy? It's probably too easy because you could just say here, oh, I see Mr. Ford, and I see this, angle B and angle L. Those have got to be congruent. Yep, those have got to be congruent. So, hey, let's make it a little bit harder for you here. Boom, going away, going away. All right, just based on what is written right here, triangle TGB congruent to triangle QXL, fill in the rest, fill in the rest. You guys have 1 minute. Ready, set, go. Fill in the rest. All right, QX. What's QX congruent to? QX. Segment QX. Somebody tell me. Right? I just want to get you hyper aware of the way these statements were in here. This stands for triangle TGB is congruent to triangle QXL. So QX, what we know, will be deduced from this using definition of congruent figures is that QX would have to be congruent to TG, right? 2G right here. Boom, right there. Or GT, right? GT, that's the same thing too. Segment GT is the same thing as segment TG. They have the same endpoints. All right, angle BGT. What's angle BGT congruent to? Angle BGT. Well, that's like saying angle G is congruent to what? Angle X, right? Angle X right there. So LXQ, right? Angle LXQ. Good to go. How we doing? Do you write them down? Write them down, right? Write down your answers. Make sure you check them out. Make sure you get the same things I do. Segment XL. What's segment XL congruent to? Segment BG. Segment BG or segment GB, right? That would make sense as well too. T corresponds to Q. So what we can deduce from this, if we knew that these two triangles were congruent given to us, is that angle T is congruent to angle Q. That's another thing we can deduce. We can deduce 6 things total, right? 6 things total. 3 congruent angles and 3 congruent segments here. Have we talked about QL yet? Well, segment QL, that's the hard one. What is segment QL congruent to? Well, that would be segment TB, or segment BT. That's fine there too. So remember, naming matters. The order matters here. And now we can visually see that our answers are right. QL, yep, that's the same length as BT. I agree. Those are in corresponding places. They're corresponding parts. So remember, these are all corresponding parts, right? Remember, what are corresponding parts again? Corresponding parts are, right, angles and sides. Okay, angles and sides. Corresponding parts is angles and sides. Okay, angles and sides. We have one, two, 3 corresponding parts here, and 4, 5, and 6 corresponding parts here. I'm doing this in red so you can't see what I wrote there. But anyways, I try to make them match up here. And that, again, is congruent figures. All right, now we have a very big moment, kind of wrapping us up here, getting us through here. So, right, I got to give you the introduction, kind of giving you that thing, and, right, kind of busting through it. It's a lot of, you're like, why is he talking so much? This isn't that complicated. You just need to practice the next few days. It's true. It's all about practicing. But we have a very big moment. And I don't want to, like, I don't want to let you down real quick. Boom, we got fireworks going right now. Guys, you've gotten to your geometric awakening. I can't wait for this. This is fantastic. I've been just pretending with you guys, just messing around with you guys for 2 chapters. This boring stuff, crazy stuff here. Stuff's going to get real right now. Guys, your minds are about to be blown. I'm telling you that. I'm telling you that. Your geometric awakening happens now. It's a big moment, folks. A big moment, because what you're getting, friends, I'm so excited for this. I am so excited. You're getting the thing that is like the most memorable thing in all of geometry. Oh my God, this is great here. This is called what is this here? Finally, we're getting to this. The definition of, oh my God, I'm so excited for this. Definition of congruent. We already have definition of congruent angles. We have definition of congruent segments, and we have definition of congruent figures we just got. But we're going to get more specific with it. We're, friends, are going to get definition of congruent triangles. Oh my God, we're going to do this definition of congruent triangles. That is fantastic. Definition of congruent triangles. Heck yeah, boom. Definition of congruent triangles. You see some congruent triangles. I dropped it on you. Mic drop, definition of congruent triangles. Well, not mic drop yet because I haven't told you the definition yet, but man, this is ever a big moment. You're going to remember where you're at, right, when I talk about this. I'm serious about this too. I've had conversations, people in college, random people from New York, from Michigan, who we were talking in college, and we're like, hey, you remember this congruent triangles from geometry? I'm like, yeah, man, congruent triangles, oh, so sweet. Congruent triangles is what it's all about. Get used to it. All chapter we're dealing with congruent triangles. Anyway, definition of congruent triangles is this. Pay attention to this. Congruent triangles are 2 triangles where all corresponding parts, angles, and sides are congruent. Oh man, huge. You're like, what? That just sounds exactly like congruent figures. You're right. It is kind of just like congruent figures. Congruent figures are figures that have the same size and same shape, and so we know that the corresponding angles are congruent and the corresponding sides are congruent. Definition of congruent triangles is just a little bit more specific than that. It's a congruent figure, basically, that is a triangle, right? 2 triangles where all corresponding parts, angles, and sides are congruent. That is the definition. There's another thing that the definition tells us. Oh, my daughter's crying upstairs because she's getting literally awakened right now, geometric awakening. But here, this is actually an abbreviation for the definition of congruent triangles that we're going to be using all book. Okay, so getting ready for it. We actually abbreviate the definition of congruent triangles. It's a sweet abbreviation, and that definition is corresponding parts of congruent triangles are congruent, or C.P.C.T.C. Oh boy, look at that down there, C.P.C.T.C. And that, my friends, mic drop, is your geometric awakening. C.P.C.T.C. Get used to it. And you're like, what is going on right now? Mr. Fortin, what is this? This is ridiculous here. Okay, so definition of congruent triangles. We have congruent triangles, okay? And if we knew the corresponding parts of congruent triangles, we know if we have congruent triangles, we know that the corresponding parts of those congruent triangles would be congruent to one another, okay? So if we knew that we had two congruent triangles, we would know that the corresponding parts of those triangles were congruent. So when we have congruent triangles and we want to say two angles are congruent between the two triangles, or two sides are congruent of the two triangles, we would use this definition by simply writing C.P.C.T.C. in a proof, okay? In a proof here. So make sure you write this down. Abbreviations of this definition commonly used in proofs are this: corresponding parts of congruent triangles are congruent, or C.P.C.T.C. You might be wondering, CPC, I keep seeing C.P.C.T.C. What does that mean? We'll practice it more. It'll stand out to you, but it's written in a bunch of proofs. You need to know eventually what C.P.C.T.C. means. And are you awake yet? I don't think you're quite awake yet, because this is kind of hard to memorize the first time through. But I'll be telling you, you'll be at like parties and stuff in college. You'll be like, you guys remember geometry in 10th grade? What the hell was that all about? And then your friends will be like, oh yeah, C.P.C.T.C. I swear to God, that happened to me twice in my life, twice in my college life. Again, a friend from New York, friend from Michigan, like it came up like in different conversations. Would be like, hey, remember high school geometry? They were like, yeah, C.P.C.T.C. That's what it's all about, C.P.C.T.C. This is used a lot in proofs. Okay, used a lot in proofs here. So the definition of corresponding triangles are when you have corresponding parts that are congruent. So if we have congruent triangles, we can say the corresponding part of those congruent triangles are congruent, or label that C.P.C.T.C. in a proof, okay? This doesn't come across with you until you start writing proofs. But just remember this: C.P.C.T.C., stay awakened, my friends. That's right, stay awakened. Those letters, right, means you're a very awakened geometry person. You know what's going on, and yeah, you know what to do. You know how to use those words, C.P.C.T.C. Because you want to fit in with your friends in college, right? Friends in college will be going to these random schools all across the nation, and they're going to be hearing about C.P.C.T.C. They're going to be talking about this. This is a great way to make friends in college, is by bringing up C.P.C.T.C. So just like, if you don't understand what this means yet, pay attention, so that you can make friends in college. That's what it's all about here. Mr. Fortin already making some college friends for you guys here. Check this one out. All right, here's how we can use C.P.C.T.C. in a proof. You might be wondering, those are 5 letters. How am I going to remember that? Man, you're going to be saying C.P.C.T.C. so much that you're going to get super tired of it in a second. But let's just see how we use this in a proof right now. All right, check it out. We got triangle ABC is congruent to triangle LMN. And how can I use C.P.C.T.C., for instance? Well, remember, C.P.C.T.C. is just the definition of congruent triangles. If I have two triangles that are congruent, I know their corresponding parts are congruent. Okay, so that's what it stands for. Corresponding parts of congruent triangles are congruent. Corresponding parts of congruent triangles are congruent. Everybody sing it with me. Corresponding parts of congruent triangles are congruent. Sing it with me louder. Corresponding parts of congruent triangles are congruent. Good. One more time. Corresponding parts of congruent triangles are congruent. Oh, yeah, that was good singing. Yeah, give yourselves a round of applause. Man, that would have been fun if we were all in the room together. But anyways, so corresponding is the first word. Parts of congruent triangles are congruent. And man, I'm definitely going to be quizzing people on that when I see you guys on Friday, because you got to know, you got to be awakened, my friends, geometrically awakened, my friends. It doesn't make sense to be asleep away from the good old geometry. You got to be an awakened soul, my friend. So anyways, corresponding parts of congruent triangles are congruent. Well, that just like if I have congruent triangles, I can say any of these corresponding parts are congruent. So for instance, I could say angle B is congruent to angle M. Right? If I wanted to say that in a proof, what's the reason I'm going to use? Right? What's the reason I'm going to use to justify this? If I have two congruent triangles, why do I know that these two parts are congruent? Well, C.P.C.T.C., my friends. It's going to appear in proofs. You're going to use C.P.C. as a reason to justify why angle B and angle M are congruent. Look, they're in corresponding places. They're in corresponding places. They're in corresponding places. Stay awakened, my friends, here. I could also say what? I could say BC is equal to MN. Reason, well, BC, right, corresponds to MN, right? They're in the same positions there of the two congruent triangles. Reason, C.P.C.T.C. Then again, C.P.C.T.C. stands for corresponding parts of congruent triangles are congruent. But you can just write C.P.C.T.C. You could just write this too. You're allowed to just write corresponding parts of congruent triangles are congruent. Your book does that too. They want to just like not just write this mysterious CPCTC. Because I'll be honest, guys, I went like a month in high school, like a month of just writing CPCTC. And I didn't want to admit it, but I had no idea what CPCTC stood for. I was not awakened. So I'm going to try to awaken you guys. What does CPCTC stand for? It's corresponding parts of congruent triangles are congruent. All right, next one up here. Angle A is congruent to angle N. Why can I say that? Well, it was given to me that these two triangles were congruent to one another. Here, like the triangle's down here, but hey, I just know this by looking at this here. What can I deduce? I can deduce that angle A is congruent to angle L. Reason, so statement and a proof. So if this is given to me, and I use this as my given, next step in a proof can be angle A is congruent to angle N. How would I justify that? C.P.C.T.C. Oh, wait, no, I can't. I can't actually state this. I tried to trick you guys there. I tricked myself right here. This one isn't C.P.C.T.C. Check this one out here. I can't say angle A is congruent to angle N. Why? Why can't I say that? They don't actually correspond to one another. Check it out here. I can deduce that angle A is congruent to angle L. I can deduce that angle N is congruent to angle C because they're corresponding to one another. Remember, order matters here, right? The way we see this out. But I can't deduce that angle A is congruent to angle N because they're not corresponding parts. They're not corresponding parts. Remember, corresponding parts of congruent triangles are congruent to one another here. Boom, can't conclude anything there. So let's get one that we can conclude. What's our reason for concluding this? AC is congruent to segment AC is congruent to segment NL. Let's see here. AC and NL, yep, NL. So those are the two vertices mentioned at the ends of the way we read out those triangles. Those are corresponding parts of congruent triangles, and we know that they are congruent. We know they are congruent. So corresponding parts of congruent triangles are congruent. CPCTC. I'm trying to drive you guys crazy. I'm trying to get you awakened, my friends. What's another thing we can say? We can just keep on going. We can go all the live long day. AB congruent to ML. Are we allowed to do that? Yep. AB is a segment. LM is a segment. LM is the same segment as ML, so they correspond to one another. CPCTC, CPCTC, CPCTC. This helps us write lots of proofs. We're going to write lots of proofs this chapter. And you actually, remember I kept saying like a lot of people don't get proofs until chapter 3. I'm hoping you're going to get it in this like understand proofs this chapter because you're going to write a lot of them. You're going to get going. You're going to kind of get to understand them, hopefully, and get some practice at least using that CPCTC in proofs. And man, you're probably like, what's going on? You just need to practice. You'll get it. All right, check it out here. This is just a summary of the section, what I just went through with you guys. Your geometric awakening. Hopefully you're awakened now. All right, number 1, congruent figures have the same size and the same shape. Same size is determined by the corresponding sides having the same length. And the same shape is determined by the corresponding angles being congruent. Fantastic, okay? So if I know one shape was congruent to another shape, right, I would know that all the angles are the same, right? Like, although that correspond to one another. Like each angle that corresponds to another angle in the other figure, they would be congruent. I would also know that all the side lengths were the same length, right? Going from one figure to the other figure in terms of their corresponding positions, right? Positions here. And finally, so we talked about congruent figures. We also talked about the definition of congruent triangles. What's the acronym? What's the thing that we can list down? It's only 5 letters. When we want to use the definition of congruent triangles, remember, congruent triangles are simply just figures that are triangles, right? Congruent figures that are triangles, right? 2 triangles that have the same size and the same shape, or 2 triangles whose corresponding parts are congruent, have the same angles and have the same side lengths, right? So the definition of congruent triangles are triangles whose corresponding parts, sides and angles are congruent. And to summarize here, the way we use congruent triangles, definition of congruent triangles in proof, if you knew it was given to you that 2 triangles were congruent, then you can say C.P.C.T.C in a proof to justify why any of those corresponding parts, be they angles, be they sides, as long as they're corresponding, you would know that they're congruent, okay? And you can just list C.P.C.T.C in a proof rather than writing in definition of congruent triangles. Mind blown? I hope so. I hope so. C.P.C.T.C, because have you been awakened? Do you know what C.P.C.T.C stands for? Oh, I better hope you do. Man, we'd be singing in class. We'd be like cheering. We'd be dancing in class. That's usually how this lesson goes. Section 3. Lots of dancing. We'd be doing cartwheels in the hallway, little parades. Man, it's usually a real good time. All right, homework. I don't know if this is what I'm going to give you for the homework or not. I have to decide that. You're doing asynchronous problem set Tuesday, also doing it again Thursday. We'll just see. Welcome to chapter 3. Let's get our feet wet. It's going to be a weird week. We have Wednesday off. That's that from now. Hopefully you enjoy this. I enjoyed filming this. This is fantastic. I'm glad we got to chapter 3. Do your exit ticket. You got an exit ticket now. Now you've listened to me go on and off about CPCTC. Go do that exit ticket. I'll talk to you guys later. Bye.